Hello, everyone. I'm Chris Katoya. I'm here today for the cadCAD community call, April 19th. Here we have Jamsheed Shorish with us, who will be giving us a preview of the upcoming GDS paper. And To do that, he'll be going through spaces, blocks, and block diagrams that is coinciding with the upcoming release of cadCAD reference. So I want to hand it over to Jamsheed. Thank you
All
so
right.
much for joining us.
No, thanks. Thanks very much for the invitation. It's a pleasure. And thanks, Chris. And just as a very minor point of clarification, the second GDS paper, the Generalized Dynamical Systems paper with Michael Zargham is not quite finished yet. But this presentation will reference another paper that we've recently finished that actually serves as a prerequisite for some of the work that we wanted to surface in applications in that paper on block diagrams. And so that will tie in, as you mentioned, very nicely to how the cadCAD evolution is occurring on the other side. So just with that brief introduction, let me give you a quick overview of what I'll try to touch on during the course of about 20 to 30 minutes of today's call. Just as a basic outline, I just want to give a few, really just a laser-focused series of pros and cons of the current version of cadCAD and kind of why that helps to stimulate this new reference implementation that is currently underway. And in particular, this notion of breaking out the earlier partial state update blocks and policies into things that are more formally blocks and spaces and what that means for its implementation. That leads naturally into a visual representation of these different components now, almost like little Legos or building blocks that snap together in a certain way. And one of the nice ways to do that is using block diagrams. We want to make sure that we're not losing anything in terms of the fidelity of what we're trying to represent by doing so, however. So we need to make sure that when it comes down to a computer implementation, that we actually can make those Legos a reality. And that leads us to a way to encode different spaces and blocks using nested schemas. And sort of the shorthand in the back of one's mind would be a JSON schema-like representation. And finally, what I'll do is give just a very short 1 or 2 slide picture of a block diagram of a state update that would be a candidate for representing how state updates would occur in the new reference implementation. And then I'll be happy to take any questions or comments from that point forward. So in the current version of cadCAD, I think one of the, or two, I would say, of the really great advantages of the system are its modularity and its composability. In terms of the modularity, you can add to the system dynamics by just creating new PSUBs, partial state update blocks, by adding another state, new participants, in a very modular fashion. So that if you find yourself looking for extensibility, it's an extremely extensible system and very user-friendly in that framework. At the same time, you want to be able to ensure that when you are creating multiple streams of processing from one state to this future state, for example, when you have many different players or participants or updates that are occurring, that these chain together really in a way that is consistent with the building of policies both within a time step and a partial state update, or by, for example, flagging what occurs when between different time steps as you move forward in a cadCAD simulation. So these are really advantages that you don't want to lose. In any kind of movement from one version of cadCAD to another, these are things you want to keep. Now, on the challenges side, some of the things that can kind of crop up when attempting to use this to its utmost are things like type safety. The composition, when you're chaining things together, it really has to compose properly. The type of an output from one thing that you want to use as an input has to match the type that's expected from that input when you compose things together. And this can become tricky when you really start to build out spaces that are very, very abstract. So not just a set of integers or the set of real numbers. Let's say maybe your state is a network. The exact configuration of the attributes of particular vertices and the edges and the weights of the edges in between them, this can become an object in its own right. And you can look at things, for example, as database entries and how they update as well. So we would like to be able to keep things sort of coherent, even as we expand to more abstract states. And at the same time, we do want to make sure that when we are composing things and chaining things together, that we don't end up breaking the system in the sense of pushing against the boundaries of what's computationally feasible. And in particular, a p-sub length, for those of you who've done some large-scale complex simulations, you can see your p-subs get really, really, really long. It can be difficult to scale for these types of complex environments. And so there is a feeling that perhaps we're bumping up against, in some cases, a composability limit. And so what we would like to be able to do is to maybe, let's say, reorient to the extent that we can to show how composability is something that can scale well. So these are not the only two motivations for creating the new reference implementation of cadCAD. There are other reasons that are just trying to make it both from a more performant point of view, something that can be used in a very efficient manner. But these are some of the ways in which we would motivate under the new reference implementation, trying to address those challenges while ensuring that those advantages of modularity and composability aren't lost. And the approach that's been adopted is to implement the state space, the admissible action spaces of participants, users who are also taking actions in the partial state update to change the state, as spaces in their own right. And we just have a classification then, almost as a taxonomy. We say, well, there's a kind of thing here, and this thing is a space. And then state updates occur as transitions between spaces. User actions that are conditioned on one set of variables that create a new set of variables are themselves also transitions between spaces. And we call these transitions then blocks. So you have a space coming in from one side, there's a block that processes the information from that space and then provides some space on some sort of output as a space on the other side. And this turns out to unify quite well with the approach for the foundation layer of generalized dynamical systems, which is the conceptual foundation for the way that cadCAD is structured. But it helps to admit these abstract spaces that we were referring to earlier, like network objects or databases, in a very streamlined fashion. So it allows us to augment the existing vector spaces approach with more abstract space representations. And at the same time, it allows us to have sophisticated but straightforward composition by chaining together type-safe blocks. And the idea here is to ensure that that's done in a consistent fashion, a coherent fashion, but also in a performant fashion. And just to give you an idea of what a block would look like and how a space is organized for a block, this is an excerpt from a paper that the paper I referenced before that Michael Zargham and I have been working on, called Block Diagrams for Categorical Cybernetics. This is essentially a schematic for a block, which has on the left-hand side a domain series of spaces, x1, x2, all the way up to xn, where each of these has a type that is accepted as the type proper for that particular port or that input side. Then there's processing of that information that goes on in the center, where the black arrow with the F is, and it's a function applied to the inputs that are coming in. And then there are a set of outputs, each of which resides in a particular space, y1, y2, up to ym. These are represented as the terminals, the outputs of this particular block, and that's the codomain of the environment. So this is essentially, in a nutshell, the pieces of the components that you can build and chain together for any dynamical system that can be represented as a generalized dynamical system. And just to give kind of a feeling for what we mean by this, here's an older schematic where it wasn't as set down in its formalization of a generalized dynamical system that relies upon an initial state, little x, in a larger state space, big X, to inform both the actor's choice of action, that's that topmost block, that g of x is what somebody might choose seeing the current state, and what the system will do when it updates itself on the basis both of the state x and the actor's choice of action u, and that's in the systems mechanisms box. And this is where the state transition occurs. And inside all of this is the effect also on the admissible actions, so that when you look out the window and you see what the state of the world is, it maybe affects whether or not you can take certain actions. So the admissible actions themselves depend upon the state. And this loop then feeds back and forth as the inputs come in, the state comes in, decisions are made, and the state is then updated. And what we would like to make sure of is that this schematic that we've created for a generalized dynamical system is actually something that has more than simply a visual value as a, oh, this is just a shorthand for understanding what the math is. There's a mathematical model. We just write this shorthand up. And instead, think about making this something which is formally comprised of these types of blocks. And if we can show that we can do that without losing any information about dynamical systems, so that we don't actually end up with a system that we would love to be able to implement, but find out that we can't because the tool set is restricted. And at the same time, ensure that the tool set is actually not so broad that it becomes impossible to know, how do I start? What do I start from? And it becomes a tool which is not particularly useful. So we need something in the middle here which allows us to, in a sense, build a representation formalism that we can say, yes, we rely upon this. We know that when we pass to this type of a visual representation of what we're doing, that we aren't losing something in the process. And this is the motivation for this this paper that we wrote, really about a formalism for block diagrams. So we're attempting then to ensure that we can pass from GDS to the new reference implementation of cadCAD really just through spaces and blocks and nothing else. And so the question being, do we lose anything in this passage in either way? And it's really a formal approach, basically the same question being asked a slightly different ways. How far can spaces and blocks take us in this representation? And what we found on a formal level is that it's pretty far, as long as you really respect the fact that these blocks have to snap together, that there's type safety, that the output of one block, when you want that to be the input of another block, then that type of the output has to match the type expected of the input. And without going into too many of the details here on the math theory side, what we leverage is a very nifty way of sort of a meta abstraction level of looking at objects and relationships between objects called category theory. And this is the abstract universe where these spaces and blocks, they're leveraging a particular categorization of objects which are types. So by looking at how types snap together and how you can pass from one type to another, we're able to build up a formal representation of the visual block diagrams that you've seen so far. And just to give an idea of how that would look when you start to build out that formalization, this is an example of a block diagram that looks at a control system. So very similar to the GDS environment, except in insofar as we're actually looking at how a controller is affecting or manipulating a plant with a particular sensor that tries to understand what is it seeing from the plant as output. Those readings then are taken by an observer and used perhaps as an estimate, perhaps with error, to adjust the controller to then match up to a particular target that is desired. And this is at least evocative of the notion that we have these input ports, these ability to take things from one side and provide them through the logic of the block, these output ports or terminal ports that give us, or terminal outputs that give us the ability to make a mapping between states, between spaces. So we have a domain coming in from one side as an input and a codomain for the spaces coming out as an output. Now that's all fine and good from the side of generalized dynamical systems and their representation as block diagrams, but we need to go further because we need to ensure that the block diagram representations themselves provide us the ability to actually do something in cadCAD, to actually make an implementation. And the glue that connects these representations to the implementation side of things is another category of objects and relationships between them, called what we call the category of nested schemas. This is this notion of having a JSON-like structure. The schemas themselves, they retain the space's flexibility for the designer or the developer or the implementer. So you're not sort of shackled to one particular inflexible schema representation. There can be many. And they support type safety enforcement for the blocks. So you can actually encode what it means to be type safe within the schema itself. And this then allows you to have block-to-block composability, both within a time step as a partial state update and across time steps when that state has changed. And this is what really allows that passage from a GDS formalism to its representation by mappings between schemas now within the cadCAD reference implementation. So we're ensuring that we don't lose anything by moving to the space and blocks side of things for GDS. And then we are ensuring that we can represent spaces and blocks, and spaces in particular, the space representation, as a schema. To give an example of the kind of environment, it's very similar to what you've seen. Again, if you've seen a JSON schema before, here we have in the middle of the slide a record of a user with particular values for the keys and a key value pair, ID, name, and email. And as you can see, the values associated with these keys can either be a type, for example, the ID's type is an integer, or it can be another record, another sub-record of a key value pair. For example, name then moves to a first and a last key, both of which are strings, and so on. And you can see that within this type of structure, you can repeat certain patterns that exist that can be likened to, and in fact can formally be shown to be the same as, a subspace of a space associated with the shape given by the record. So if you interpret the shape of the space of the user as the middle record, then you can see that there are two tinier copies of another pattern, which can be likened as a subspace, that looks like email, where we look on the far left side in blue, the email has a key value pair of name and web domain, and we see that repeated in the value of the email key for user and the recovery email key for user. And by exploiting this formalism, we're able to build out a way in which these nested schema can represent spaces that are not just vector spaces, not just a set of integers or the set of real lines, a set of real numbers and so on, but very abstract spaces. In fact, abstracted up to the point of being able to have a representation as a JSON schema, or as a schema that is built with these branches and then terminal leaves of types. And so what we end up with then is this type of environment for a dynamical system. This becomes then sort of a catch-all for the notion of a system that has, on the left-hand side for the ports, x1 to xn as the state. This is the state of the system. You'll see that they're repeated on the terminal side, x1 to xn, and that they feed back into the terminals of those particular entries feed back into the ports. That's the state update. When you go to xt plus 1 is f of something something xt, this is the feedback loop that is occurring every time you cross over a time step in a model. In the center there you see f, and now I've put a little subscript there for delta, meaning that f is dependent upon a parameter. For those of you who do parameter sweeps using cadCAD, this is where the parameter sweeps would come into play. And in fact, I have some additional text to kind of elucidate this. So parameter selection under uncertainty or Monte Carlo sweeps would be affecting that delta parameter inside. And you would think then about the mapping that is moving these x's across each other as the policies of a partial state update block. The partial state updates themselves are these arrows feeding back. And then you'll see two other things left on this, which are the way in which you would actually, in a way we already do within cadCAD, but the way you would like to be able to place, on the left-hand side here, constraints or assertions, not just initial conditions, but also conditions that occur throughout the evolution life cycle of a dynamical system as boundary conditions for the system itself. And so we would add that in as something as an input to the port. It's not strictly speaking a state. There's no feedback, but there is the ability to morph or to mutate this every time step. And on the other side, on the right-hand side, you see an output terminal for a space Z. And here we're looking at measurements, the ability to kind of peek inside the box of this block and say, that's what's going on. I want to measure this. I want to be able to understand that. And these key performance indicators, KPIs, or metrics can then be used to inform, for example, parameter selection, the changing of delta, for example, or simply as ways of understanding what's happening within the system. So all the usual ways in which we build out these ways to observe and these ways to influence for the KPIs and metrics or the constraints and assertions are formalized in this block diagram environment, where each of these spaces, x1 to xn, y, and z, are represented by nested schemas in the actual coding in the reference implementation for cadCAD. And that's essentially it. That's basically the work that we've done up until now is to ensure that we have this bridge that's built between generalized dynamical systems and its cadCAD implementation. The next steps that we're working on now, of course, are not just in the work on the reference implementation that Emmanuel and others are performing, but also to ensure that we have good enough use case or case studies that we can actually put out there. And that's actually the goal of this second GDS paper is on applications to be able to show how you can build certain dynamical systems using this framework and then feel that it's consistent and as mentioned that it is coherent as a methodology. So that's it. So thanks very much for your time, for listening.
Wonderful. Thank you, Jamsheed. Uh, I'm curious if there's any questions or comments.
I thought the presentation was really good. It really summarized all of the formalization that we base the reference implementation on. I don't have any specific comments or questions, just congratulations on the presentation, Jamsheed.
All right. Well, thanks, Emmanuel. That's great coming from you. I mean, it is, I think, important to ensure that for everyone who has been heavily involved, either as developers or as users of cadCAD, feel comfortable with the notion of in essence, a closer connection to the underlying theory around the dynamical systems, even if you don't necessarily think of your systems as GDS, at least knowing that there is a way in which it can be formulated, and then perhaps maybe as an advantage, being able to draw a diagram or diagrams can then help to make that passage to this new reference implementation somewhat of a let's say easier, let's say less of a lift from the current framework. And insofar as another potential advantage to this approach is that it provides a visual interface between the dynamical system on the one side and its implementation in the reference framework on another, then hopefully that can maintain engagement and in the longer run, of course, increase engagement in the new version.
Yeah, absolutely. What I really liked here, I would love to borrow these diagrams for our official documentation because what I really appreciate here was you showed sort of like very early versions of it.
Mhm.
And what you have here now, it really brings to light, I think, more of this idea of like, hey, the relationship between the domain and the codomain from the left and the right sides, um, you can visualize them in your head more of like a manifold, um, which I think is helpful for me. I'm very visually inclined, um, so
Definitely. Yeah,
yeah,
that's true. In fact, you can indeed formalize this as, and in a way, we kind of are leaning in that direction by showing that instead of just having the ports be just one monolithic, the space, we broke
yeah,
it into x1 to xn. And so you're quite right. You could take slices of these and say, hey, I've got a projection of my manifold in 1 or 2 dimensions, and maybe that's the state space part that is classified as a global state, a state that everybody has access to, while
right,
maybe X3, X4, X5, you check the projection, you say, well, those are really local states, but we still need them, of course, because we want to update these.
yeah.
That's a nice approach.
Yeah. So yeah, definitely need to follow up with you, and whenever you're comfortable, sort of releasing the diagrams, we'd love to just incorporate it as part of the core documentation.
Well, excellent. Well, I think it's certainly fine on my side to, and I'll of course double check this with Zargham, but I think it's fine at this point to at least have the presentation available as a PDF, and if we decide to sort of pull those out pull the figures out for documentation, then I think that shouldn't be a problem. But always making sure
Awesome.
to double check with the co-author.
Yeah. So yeah, when we have the go ahead, we'll release the link to this video as well as the materials that you used for the presentation.
I'm
Excellent.
also just curious, with having these sort of inputs and outputs defined, would that help for sort of like model composability? Like I'm just looking forward to sort of the drag and drop like visual model design that we've discussed in the past, as forthcoming cadCAD sort of user experience. And I'm curious, like,
Yeah.
how the blocks in these sorts of things will help to define, sort of required inputs, required outputs for plugging different models, even within one model, or building like meta models involving multiple cadCAD models. Do you see this helping to sort of define those inputs and outputs and make it more easier to plug them together?
I think that's a great question. I think this is it's nice in the sense that when you look forward to kind of again lowering the bar of adoption, having a drag and drop environment would be outstanding. And in this environment, you can kind of think of it as I try to harken back to video games both in past and present, where if you're trying to place an object into a landscape and the landscape doesn't accommodate it, say you want Age of
Hmm.
Empires, you want to put a farm in there and it's red, you can't put it there, you can't put it there, you're getting frustrated, you rotate it, oh, it's green now, I can place it there. And you could have the same environment where you would basically have models that had certain inputs and certain outputs, and if you wanted to compose them, then as long as they were not type safe, it would stay red. You'd be shuffling it around, shuffling it around. You may have to go back and redefine the way in which the ports are accepting different types of input, or even generalize different types of inputs in order to get them to go green and then snap together and have the composability push through. So that might be one way in which this sort of focus upon type safety is really not something that is optional in this case, because you do want your blocks to make sure that they only operate on things as defined, but it's not meant to be a burden or an overhead. And so I think here's a low-hanging fruit that when you look at composability,
Exactly.
this helps out a lot.
Yeah, and,
Cool.
and fortunately, at least on a first pass of the visual cadCAD uh, endeavor, we can just borrow from the established user affordances and patterns that have been established in the space already. So, uh, as we've discussed, I think a number of times in the past, like a lot of people are drawn to machinations as like a first like pass into some level of system modeling, and so we can borrow a lot of those established design patterns, which have existed even before machinations. Um, and they're just basically building off of block diagrams, and then you can get like wiring patterns off of those. Um, and that should be sufficient for people getting started on their journey. And then what you do is you allow like custom block construction for people that are a little bit more facile with the concepts and with building uh, uh, the models. If they still want to do it in a visual format, you'll probably graduate to a point where the visual developer is too slow for building, but it is useful for some level of debugging and just sort of sanity checking.
Yeah.
Um, and so then at that point, like, that's sort of how I envision users of cadCAD when we have the visual builder component as well, as where it's like, hey, you're first starting this thing, the visual components are really helpful. Then it's sort of training wheels to get you off of relying on the visual components too much, and then you're just mostly working in the code because you can maintain the image in your head better, and it's just faster to work on a keyboard. But revisiting the block diagrams is helpful for sort of reasoning about the model you've created at that point.
Yeah, I think that's nice. You can leverage them both. In fact, I think that
Yeah,
as we know, we haven't really placed any kind of restriction on what goes inside a block. And
yeah,
as you mentioned, it
exactly.
has to be something which is eventually code based. And certainly when you want to optimize, you really need to do that at the code level. But all of the connectors could be
Exactly.
representing simply code snippets. So that if I, pick an arrow and I return it back to the from the terminal to the port, and the type is okay, well then basically the environment would just populate the scaffolding for that code
Exactly.
without me having to put anything in there. So I think if we could
Right,
provide
because we have the type safety and the composability, it sort of implies a lot of templatization of sort of base primitives that, as you described at the top of the call, we're trying to create a system of Lego blocks here. Um, and so, we'll have a bucket of Lego of brick types that people can throw together in order to get a model that runs. And then, you know, at the optimizations level, then you might be needing to get into like at the code level, but you can get pretty far and have a running thing that is useful without code is, I think, the vision.
Yeah, I think that's a great vision to have.
Cool. Wonderful. As we wrap up, is there any closing remarks?
From my side, I guess I would tell everyone to kind of stay tuned as the reference implementation continues development, and certainly continue to watch the space, both from the cadCAD side of things and also from the BlockScience side of things, as more and more of the underpinnings are explored. As I mentioned before, that second paper that's in progress is really to look at applications, and we're going to be selecting a few examples that hopefully the community and readers will be able to engage with. And then the final paper in that three-paper arc will be firmly on implementation, and it will really be focusing upon a lot of what you've seen already in this presentation. But again, utilizing and leveraging those applications in the second paper, and then showing how those are actually implemented in a reference implementation.
Wonderful. Cool.